Enough freezing? That's what's all about.
A couple days ago.
All right, guys. So, if you missed last class, I feel bad for you, but thankfully your teacher records his lectures. Highly recommend you go back. But let me do this. Any specific questions from homework before I get into my spiel yet?
Maybe 63, 4.1,
63? Oh, yeah, good. I love this problem. And I so would. One big thing is, this is going to seem unrelated, but just bear with me, John. How would you factor this? Yeah, take an x squared. I love it. 1 plus x, but I don't know. What about, so how would you factor this then?
1/2.
Why did you take x squared out? Because 2 was the smallest exponent. So what would you take out?
the negative 1/2.
Negative 1/2. The smallest exponent, let's see, right? So x to negative 1/2 comes out. I'll do this plus 1 plus
Negative. 1.
It's a negative 1. It's a negative 1. That's a negative 1.
X. 15.
There you go. Cool. When you take something out, you divide it out. X to the 1/2 divided by x to the negative 1/2 is x to the 1/2 plus 1/2. It's a whole x.
Can you do that with whole numbers so we can see what happens?
Sure. I understand. So 3 minus 2 is 1. There's a quicker way to do it. 1/2 minus negative 1/2 is 1. There, see?
Oh, I see.
So it can't, the idea can't change. Why did you think 2? Because it's smaller. Now what does that have to do with this problem? At some point you're going to have to factor something with exponents of a minus 1 and a and b minus 1 and b. You take out the smaller exponent like you always do, right? So they give you this problem, they say find the local, what exactly, how to say it? Find the maximum value of that. And if it has a max value, what must occur there?
The derivative equals 0.
I love it. So we start by kind of doing it backwards. You find all the places where the derivative is 0, and then we figure out a way to check to see if it really is the biggest place, the highest place. So you just take the derivative. That's all. So how do you take the derivative of this? What do you have to use? Product rule. I love it. And within that, power rule. So when you do this guy's derivative, what happens there?
A minus 1.
And you leave this guy alone, right? We'll put a plus there for right now. Leave this guy alone. What's the derivative of this going to be?
Negative 1.
Times chain rule. Alright, so I wanted to do that much for you because that's a big thing to miss. It messes everything up after this if you do that wrong. So you end up with ax to a minus 1, 1 minus x to the b, minus b x to the a, 1 minus x to the b minus 1. So this is what I meant. You have to, how many x's can you take out?
You can take out a minus 1.
A minus 1 x's, because it's the smaller power. I don't care how ugly they make the powers look. If there's a way to tell which one's smaller, that's the one I take out. Because that's what I do all the time. Right? We just don't even stop to think about why we do that, really. So we can generalize it. But this happens a lot. And I love doing this because you take that out and it fills in this other dude. Makes it a whole x. Aww. And that happens so much in math, where you do something that makes part of it become a whole thing, and the other one's just a number. That's awesome. So here, you next step would be you take out a minus 1 of these. How many 1 minus x's can you take out? B minus 1 of them. I like it. So if you take a minus 1 x's out, how many x's are left here?
1.
1. I love it, because there was one more than that already there. How many more x's are there here than there are there? One more. So if I take this many out, there's going to be that one extra one left here. And the same thing's going to happen with these guys. That's all I'm going to say. Is that enough?
Yeah.
Okay. So everybody's got this right at the beginning. At least one of you guys I know has got the answer because we did it earlier in the office. Okay. Any other specific questions? Oh, yeah. You borrow top of there?
Yeah.
Where is it?
Yeah.
Oh, well, I like it. Damn, Jeff. At it again with the joke about the calculator. Alright, so we focused yesterday mostly on local maxes and mins. So today I want to break it up into what do we do if it's absolute max and min. So for local maxes and mins, it kind of sucks because I got to test it to make sure it's a max or a min. You guys with me? So that's what we focused on yesterday. Today we'll do another one of those problems just for review, but I want to start with something less technical. Let's see which one I want to look at. Yeah, I want to look at, let's do number 5. Sure. If you would, that'd be great. Maybe. Is that all right? You guys can. All right. I'll bring out the little candles. Oh. Steve, what are you doing? The show is starting. Come back in. All right. So, somebody tell me the location of how many local maximums are there?
There's 2. Oh, there's 3. 4.
It's interesting. So where are they? At x equal what? So x equals 1, there's no local max. Because the local max, what it would be, is it there? No, so there is no local max. Let me let that sink in.
You know there's that dot there?
It's not there though, is it?
No.
So that's where the local max would be, but is it there? So there isn't a local max there. And in fact, really think about it. It wants to be what? It wants to be 2, 3, 4, right?
Yeah.
Right? Showing off my counting skill. So it wants to be 4, but it's not quite 4, is it? How close to 4 does it get? 3.999. So anytime you think you have the maximum, just add another 999 on it. Do you guys understand? There's no number you can tell me that is the maximum, because it would have to be 4, and it doesn't get to 4 there. Too bad. All right, you guys. So it kind of makes sense. It can't be a maximum if it doesn't exist there, if it's not defined there. All right. Yes, sir.
I saw this problem before, and I think over here, absolute maximum and local maximum, they're the same.
Yes, they are. We'll get in there. All right. So is everybody cool with that? So that, hopefully, is very kind of obvious. The only candidate for it there would be that, and it's not even there. So it can't be the max, right? Okay. So a maximum actually has to be a value that the function takes on, and it doesn't take on the value 4 in here. All right. So where else is another candidate? There's definitely one where x equal to
4.
Yeah, x equal to 4 is definitely. It looks like it's going to be, and it does get there. Yay! So that's the place where the slope is 0 because it is a max. Definitely, it's the biggest one locally, right? So that's a local max. We're just talking about local stuff right now. Anywhere else is a local max?
Or is there?
6.
Where's the point?
This can't be. Because does the derivative exist here? No. Why doesn't the derivative exist here?
No limits.
Because it doesn't agree from both sides, right? So that is also not a local max. All right. So what does it take to be a local max? The derivative, if it's a max, the derivative there has to be 0. Well, does the derivative exist there?
No.
No. Right? All right. But, so, what about absolute max and min? Let's talk about min. I skipped min. Where's there a minimum?
2 and 5.
Yeah, here it's fine. Now here it's a little cusp thing. So I'm trying to remember this one exactly. The derivative doesn't exist here, but that's another place there's a critical number. Here, that's a freaky location. Let me think about it for a second. Now, let's talk about this. So here, there's definitely a local min, right? Because it certainly has a 0 or undefined. And here's 0 slope. It's the lowest point in the local area. Here, there's definitely a local min. Yeah, this is a local max. Because the derivative is undefined, but that's the location of a critical number. And in this area around it, is there anything bigger than it? No. So that is a local max. I like that. That does work. That's a local max. Why was this not a local max? Because it's not defined where it would be, right? Where it would need to be the max. I like it. All right, so I was getting those two confused in my brain. So that's fine. Local max, local min, local max, local min, no. How are we doing so far? Now, absolute max and min. All right. Well, this is a little bit not quite what I wanted, but too bad. So what do you think, a gut feeling? Is there an absolute maximum? Yeah, and like John said, it happens to also be where a local max is. This thing makes sense that very often that's going to happen. The local max might also be the absolute max, possibly. But there could be something that's even higher, right? But there's a very good chance that the local max or local min is going to be the absolute max or the absolute min. Yes?
Would we be wrong if we just wrote local max on there?
If the problem with this specific problem says find all the local maxes in local extrema and absolute extrema. So you have to identify that as being both.
Okay.
I like it. If you just call it absolute max, that kind of inherently means it's a local max, right? But you got to be careful of that too. We'll talk about that. That's not always true. Is there an absolute min? What's your gut tell you? It's kind of related to that local max not really being a local max.
On the left side of 7?
No, it gets below. How do you mean? So at 2, it gets lower than this, doesn't it? The outputs get lower than that.
So on the left side of 7 is the absolute min. Because
this is where the absolute min would be. Is it there? No, so the same idea as that. There is no absolute min on this problem, because if you think you got it, you can always get... Oh, no. So what is this? This is 1. So it's not right at 1. So where is it? It's right next to 1. That's a weird idea in math, because what's right next to 1? 0.9999999999999. So if you think you got it, just add another freaking 9 on, because you can do that forever. So is there an absolute min? No. Because it's empty where it should be. Does that make sense? Yeah. So the beautiful thing now that's the idea behind local extrema and absolute extrema. So how do you, let me see if they have a different situation over here.
Number 6.
Steven, now I can't see shit. Can you turn on? Thank you. There it is. Alright, this guy, does it have an absolute min? Yes. Where?
4.
4. I like it. X equal 4. The absolute min is 1. Does it have an absolute max? No. But notice, what I really wanted is if this was filled in, would that be an absolute max? Yes. Everybody cool with that?
Yes.
Is the derivative 0 there? No. So the absolute max and min could occur at an endpoint, because then maybe the function just stops there. Alright, so before you guys get too freaked out, the beautiful thing about absolute max and min, the work required is much easier than the work required for a local max and min. So let's do an actual problem. Let's find the absolute max and min of a problem. What's that?
We got a question, but I got an answer.
Oh, beautiful. I love when that happens.
So in number 9 in our homework, so when we draw absolute max should go like this, or like you said.
Sorry?
So you said that in number 9,
Yeah.
absolute maximum. So it should be like you said, like goes out.
There's a lot of different ways to do this. The most general way is just to make this at x equal 5, to make that be the highest point. I mean, that would be the absolute max.
Can I draw it like this?
Like you say.
Oh, like it's an endpoint. That would be the other way, because I don't think they tell you. Yeah, you can say that's an endpoint, totally. Or you can say it's defined everywhere, just make that highest bump there at 5. I like it. So that problem, if I wanted at 5, and real quick, when I say where is something happening, that's an x value. When I say what is the value, that's the y, that's the output, right? So when they say at 5, that's x is 5. At 5, something's happening. So they don't tell you what the value is. You can put it wherever the hell you want to. They just want that to be the absolute maximum. So 2 ways you can do that, really. One way is just not even worry about the rest of it. Just blah, blah, blah. And then just have the highest piece be right there at 5. And say it keeps going down forever and so forth, right? Down forever. Or you can have this 5 be where your function stops and just make sure that it's the highest it gets.
Yeah, I do it like this.
I love it. That's fine. They didn't specify what the domain was. So you get to specify what your domain is. And there's no other points higher than 5 they wanted something to happen at, so that's beautiful. I love it. Yes, sir?
So because you can't have a local max min or extrema at a point that's right by an empty spot, that means that you also can't, like, so for example, what we saw at 7, it's just less than 7. That's not an extrema. So does that mean that infinity also can't be an extrema as well?
Exactly. I like it. Yeah. Because you never get there.
Like x squared, for example, right?
Yeah, there's no absolute extreme, there's no absolute max on x squared. There isn't. Because if you think you got there, you can keep going. It's the same, I like it. So it's the same idea. If you think you got it, you just add another 9 on. Well, if you think you got this, just double it. You didn't get it. Too bad for you.
Yeah.
I like it. Okay. Oh, Steve, can you?
I was just gonna say, if there's no local max or min, but there's 2 and 4 like critical numbers, how would you go about that?
Oh, so John actually gave us. No. I was thinking. Then what would be neat is if they said no local max or min, but there is an absolute max. I thought if they were asking that, then John gave that away. I don't think that's what that one says, is it?
No.
Yeah, it did say. It doesn't say local max at 5, does it? So that one way I did, it wouldn't necessarily work, but it doesn't say there isn't a local max at 5. I mean, so I don't know. There's a little leeway there. You guys kind of with me?
I was trying to look at
Yeah, I know. So the next one says no local max or min, but 2 and 4 are critical numbers. I love it. What's the easiest function that has a critical number at 0, but it isn't actually a max or a min? X cubed. X cube's got it gets flat there just to really overstate it. It goes flat there, but it's not a max or a min. It just kind of, freaks me out for a second. Just tricks me. You guys understand that? Is that cool? All right. Thank you. There you go. Just gave that one away. Okay, so let's try one right out of the book here. Let's do. Yeah, I like this one. Yeah. So the instructions say find the absolute max and min. The beautiful thing about when they ask you for absolute max and min, you just find the critical number. So tell me, where could the absolute max or min occur? Where could it happen? It could happen at one of these kind of places, right?
Yeah.
Or it could happen at the endpoints. So what boils down to is find your critical numbers and then just find what's the value at the endpoints and the critical numbers and see who wins. That's it. So let's try it. How do I find my critical numbers?
Take the derivative.
Take derivative. Derivative.
1
Minus
I like it. Alright, it's x to negative 1, so it becomes negative x to negative 2. I like it. Cool. And then what do I do with that to figure out the critical numbers? Can anybody see what it would be? No, let's not. 1 minus 1 over x squared equals. Is that it equal to? 0. I like it. Is it undefined anywhere? Let's start there.
No.
Because where are my critical numbers happening? Where it's undefined and where it's 0. I like it. So where's this undefined? Yeah, x equals 0, it's undefined, but why is that not going to become a part of this problem? Because
The domain is.
the interval is from, where'd it go? There it is, 0.2 to 4. Let me stop right there for a second. So when you're doing absolute extrema, they got to give you an interval to work on so you know where your endpoints are. Any critical numbers that happen outside of there, you don't care about them because they're outside of the place this is defined. So 0 is below 0.2. I don't have to worry about it. If another critical number was 7, I wouldn't have to worry about that. Right? I'm not saying it is. It's just in case it was. So what about where's it equal 0?
Plus minus 1.
Yeah, exactly. I was hoping you guys could see it. 1 minus 1. What makes this 1? 1 or negative 1? Right? So how do you actually do it if you want to do it directly? X squared equals 1, so x equals plus or minus 1. Alright, both of those in the interval.
Yep. Like,
Only 1.
Yeah, positive 1 is. Negative 1 I don't have to worry about. So what are my entrants into this contest? I've got x equal 1. I've got x equal 0.2 and x equal 4. Now figure out what the values of the function are. Because what's the question here? What's the biggest output and what's the smallest output? Well, I found all the places that might occur. The critical numbers and the endpoints. Now you just plug them in and see who's biggest and who's smallest. It's almost too nice to believe. Maybe. So when you plug a 0.2, where am I going to plug a 0.2 in?
The original function.
The original, yeah, I got to know what the value is. Right? So when I plug a 0.2 in there, which is 2/10, 1/5, I get 1/5 plus 5. If you want to do it that way, or just plug in the calculator. Either way you do it, you get 5.2. Oh. Here I get, what's f of 1? 1 plus 1. That's crazy.
wow, we got it all back.
And what's f of 4? 4.25. So who won as the absolute max?
0.2.
0.2. So this is the absolute max. And who's the absolute min?
1.
Yeah. So and one endpoint was the biggest, and at the critical number in the middle was the smallest. And this guy was just there, right? He gets the participation award. You participated. Woo. That's exactly how you can show me the work for those problems. Get the critical numbers that actually are in the interval that they care about. Endpoints, critical numbers, check to see who wins. Yeah.
This way works for closed intervals, right?
Yeah, exactly. There wouldn't be endpoints for an open interval. So it would be kind of silly for most functions to talk about if I have an open, if it's defined everywhere, negative infinity to infinity, and ask about absolute max or min, because most functions are going to do some polynomial kind of thing eventually. Does that make sense? Some functions it would make sense because you can have a dampened sine function. There's going to be a place where it's biggest and smallest. All right, I like it. Do you guys follow that? But polynomials and behavior, the endpoints would never come into play. So it wouldn't make any sense. I like it. So all of these problems, notice how they all give you intervals. Cool. Okay, maybe. Is that cool? You guys get that? The absolute maximum, beautiful. So much easier. You still have to find the critical numbers, but that's relatively easy. You don't have to do any first, second derivative test. You just have to plug them in and see who's biggest, see who's smallest. All right. I like it. So that's the first part of today. Let's see. Let me let you guys try one on your own.
Oh, wait.
Yeah. Well, that's the first part of me talking about stuff. Now you guys do some. Which one do you guys want to do here?
The one that was...
Which one do you not want to do?
That's a trick question.
I knew somebody would figure that out. Here, do
61.
do 60.
60, okay.
So same question. Find the absolute max and min
He was going to get us back.
on that interval. I was waiting to see if somebody would beat you. Don't want to do this one. All right, do that one.
Yeah.
Such a teacher thing to do. Shit.
You want to learn it all?
What the hell, man?
Should I write that?
Just looking to do
60.
125,
Wow.
Schedule, right?
All right, let's see.
Get, the minimum was 0.5. The max was 2.
So what's the derivative? It's undefined where?
Zero. Nine and one is zero.
What's up?
No, add x plus 0 or something.
Sorry. So it's undefined as 0, but 0 is
Not in there.
not in there, so I don't have to worry about that. All right. And where's the derivative equal to 0? At 1, I like it. So it's almost like that last one, except it's not squared. So we just get x equal to 1. So that's my critical number, and that is in the interval. So then what are my contestants? Yeah, so I got to look at f of 1/2. F of 1 is in the middle, and f of 2. So it kind of makes sense. I mean, if I have a function, I'm not saying this is what this looks like, but if I had a function that started here, did this, and then went there, the critical number would be the absolute max, right? And then this endpoint would be the absolute min. This would just be there, right? So that's what happens a lot with the intervals they pick, is they pick it in such a way that they pull this side up and pull this side down. So the middle is going to be, the critical number is going to be something, and one of the endpoints is going to be the other thing. It's not always going to work, but that's kind of like visually what's going on with a lot of these problems. When you plug a 1/2 in, what do you get?
1.19.
One who?
1.193.
1.19. When you plug a 1 in, you get 1. When you plug a 2 in, 1.33. Blah blah blah. Okay. So then, where's the absolute min?
1.
Yeah. At 1, the min is 1. Bam. And the max? 2. Bam. I like it. So this is the kind of work I want to see. You got to check everything and then circle the ones that actually are the extrema, the absolute extrema. I like it. All right, so let's do a review of local max and min. Oh. So let's see. Whoa, that is really zoomed in. All right. Let's look at 35. Let's look at 31. Actually, wait a minute. Let's look at 138. Yeah. Boom, boom. All right. Steve, can you turn on the... Thanks, man. All right, so 30, what is it? 38?
That's cool, man.
What? Were you going to answer my question for me? Or I don't want to know. Whatever it is. So to find the local max or min, and when I find the critical numbers, what exactly are those?
That's where the derivative is.
That's how I find them. But what are they? What could they represent? I kind of gave it away. Possibly, right? They could be the location of local maxes and mins. It could be with the turning points. I like it. Could be, but not certainly. Just like setting the second derivative. We talked a little about the second derivative. Saying the second derivative to 0 is not necessarily an inflection point. It's just where they might be inflection points. I just want to get that out there because I don't think I said that fully yesterday. So when I find the critical numbers, that's why we have to have some kind of a test to tell if it's actually a true max or a true min, or is it just tricking me out, right? So take the derivative. What do you get?
1/3 x minus not negative 2, sorry.
Plus
X.
I don't know if you guys remember, but to do this rule, when you take the derivatives with fractional powers, 1 minus 3 is negative 2 over. There you go, right? Negative 2 minus 3 is negative 5. I mean, do you see that shortcut? It's beautiful. Right? Or don't do that if you don't have to, but it's there if you need it. It's kind of nice. And is there anywhere this is undefined? At 0, because these are negative powers, right? They're negative powers, so they're really on the bottom, aren't they? So at 0, this is certainly undefined. So my critical numbers include anywhere where f prime is undefined, and that would be